Okay, this is a fluid mechanics problem, and we are solving problem 7.26. So the problem gives us a diagram, and we see that we have the variable names here. So capital D is the diameter of our pipe. The velocity of the jet is V, capital V. Width of the block is B. Weight of the block is W, and the distance of the center line to the ground is lowercase d. So what we're asked to do is basically find out how the water jet makes the block tip. So the first thing we're asked to do is find a set of dimensionless parameters, and the way we're going to do that is by dimensional analysis. And then the next thing we were asked to do is find an equation for the velocity by using the conservation of linear momentum. And finally, we were asked to compare the results in A and B and check for validity. Okay, so part A, the dimensional analysis part, we were told that the velocity is going to be some function, phi, and it's going to be a function of the density, the diameter of the pipe, the weight of the block, the width of the block, and the distance of the center line of the pipe to the ground. So the first thing you have to do for dimensional analysis is look at your list and list of variables and determine the dimensions of the variables. So for example, the velocity is a length divided by a time, the density is a mass divided by a length cubed, the diameter is obviously a length, the weight of the block is actually a force, and the dimensions of force is actually mass times length divided by time squared, and the width of the block is length, obviously, and the distance of the center line of the pipe to the ground is also a length. So one important thing is that we chose to do our problem in MLT, so mass length time, instead of force length time. So knowing that, we chose to define any length as capital D for pipe diameter. We chose our mass, and we defined it as the product of the density times the diameter of the pipe. And also, finally, to get a time, we could have either used V or W, which is the weight, because there's a time and there's a time there. So, but we chose the W because the V, we wanted it to be a pi group. So here we have, since W is defined as mass times length divided by time squared, we simply substituted this mass, which is a density times diameter cubed, here, and had the length right here. So, but length is diameter, so that's what you see here. This is essentially the mass. This is the length, and then this is the weight here. So basically, solving this equation for T gives you this part, and then this part simplifies into that. Okay, so to determine the number of pi groups, if you count your list, this is actually 6 variables, and since 3 dimensions are required to describe all of these variables, which is mass, length, and time, you do 6 minus 3, and that's 3 pi groups. Now, since we originally had 6 variables, the only variables left that need to be non-dimensionalized is the velocity, the width of the block, and the distance of the center line of the pipe to the ground. So starting with the velocity, we know that velocity is length over time, so what we're going to do is simply multiply by the reciprocal of L over T, but this time using what we've already determined T and L to be. So that is essentially this step. The D down here cancels with the D squared, and you're left with this term on the right. And then similarly for the width of the block, we know that's a length, and simply to get that dimensionless, we need to multiply that multiply it by the reciprocal of L, which is 1 over L, and since we defined L to be D, you get this quotient on the right. And then for the distance of the center line to the ground, which is lowercase d, it's the same manner, so you basically have the same expression. So what we conclude is that this pi group is a function of these non-dimensional parameters. Okay, so now for part B, we have to verify that our solution to part A is a function of certain parameters. So we have to use conservation of linear momentum. Okay, so this is the formal definition of the conservation of linear momentum in fluid mechanics. You have the sum of the forces acting on your control volume is equal to the rate of change of the integral over the entire volume, and that's the product of velocity times the density, and that's again over the entire volume, and you add to that the integral over the entire surface of your control volume. You have a velocity vector times the density, and here you have a dot product of the velocity vector times the unit vector. So and that's of course dA, so differential area. So for our problem, we're going to assume steady state flow. So basically anything is basically nothing is changing with respect to time. So d dt of anything, so in this case we have an integral, that's going to be 0. So basically we have the sum of the forces equals our control surface integral. So it was necessary to define a control volume, and here in red and dashed lines we define our control volume. The only force we said that was acting on it is Fx, and that's actually acting in the opposite direction of our defined unit vector, which is I hat. And so here you have the section 1, which is the entire face here, and then section 2 is the entire face here. So basically the unit normal to the surface at section 1 is n1 hat, and it's defined here, so it's in the negative I hat direction. And so continuing, so n1 is basically defined here. Velocity in general is in 3 directions, so you have u, v, w in the I, j, and k directions respectively. So at section 1 basically you have v is actually equal to u I hat. And so of interest to us is the dot product of v and n1. So knowing that n1 is basically negative 1 I hat and v is u I hat, you have negative u. And to determine this part of the integral, you have to do a dot product of the velocity vector with the unit vector, and that simply becomes negative u times the area, so that's pi capital D squared over 4. Okay, so the integral that we're interested in solving it is actually a sum of 2 surface integrals, and it's basic since we have fluxes at face 1 and face 2, but there's actually no flux in the x direction for the second face. So basically that this becomes 0 altogether, and the resulting expression is simply this equals to that. So so basically we already know that the velocity vector in the x direction is simply u times rho, and then times our product, which we recently calculated. So v1.n1 dA is simply equal to this. and the sum of the forces acting on our control volume is simply negative Fx, and it's negative because the way we assumed Fx acting is in the negative direction of the I hat. Okay, and here we're just simply substituting, just calling u equals v, and then plugging that in and canceling the negatives. And then we're going to call that equation 1. So, okay, so next, to find the force that tips the block over, it's a simple statics problem. Basically, we're doing the sum of the moments, and here we have a nice little diagram showing point O is down here, and you have two forces acting on our block body, which is the weight and this force due to the fluid. It's an equal and opposite force that acts on the control volume. So basically, we're defining our positive moment in the counterclockwise sense, and that essentially gives us this here, and solving for Fx gives us equation 2. So that's the weight, the width, and this height here. So okay, so setting 1 equal to 2, as we recently defined our equations, you come up with this expression, and next, basically we're solving for v here, and we're isolating v squared, and then basically take the square root of both sides, and you're left with this expression here. So this is the result. It's shown there. Okay, so for part C, we have to compare the results from A and B. So from B, that was our expression we concluded from the conservation of linear momentum, and that we started to reduce to try and make it dimensionless. So we simply, since there's a d squared up here, we basically can take this d out, and then we can break this square root into 2 square roots, and then basically take this d over here, take this over there, and you get this, and then you get this same term. So it checks. These are actually dimensionless, both of these. So to show you, basically, velocity is a length over time, the diameter is a length, the density is a mass divided by length cubed, and then the weight is mass times length divided by t squared, but that's in the denominator, so we show it here. And this is simply, the only thing that has dimensions here is b and d, and those are both length, so that this side is actually equal to 1, and this side is actually also equal to 1. Here you have L squared, right, over T, and then here the result of this radical is T over L squared, so it checks, it's dimensionless. So basically what we concluded is that the dimensional analysis agreed with the conservation of linear momentum.